directly to the next part, which is the Kalman filter and extended Kalman filter. This, the extended Kalman filter, or the Kalman filter, is one realization of the base filter, and was one of the first ones which was actually used, successfully used also in the context of the simultaneous localization and mapping problem. And so just to kind of keep that in mind, what was our goal? We wanted to do state estimation. We want to build a map of the environment and estimate where the robot is in that map. And so our state space is the position of the robot in the environment and the map of the environment. It's kind of just to give you the overall picture. We won't go into the details of how to implement the SLAM system with the Kalman filter today. This will be done next week. Today is a more kind of general introduction to the Kalman filter and extended Kalman filter. Of course, it's just 1 hour, so it's maybe a bit short, but some of you have heard that already. And so I try to cover all the important facts for you, but there's also a lot of background material I can give you for reading if you haven't understood one step completely. And you can also come to my office, ask me questions if you need more details on one or the other steps. So again, the base filter, we have 2 steps. We have the prediction step and the correction step. And these are 2 steps you will now see in the Kalman filter, how they are realized. The Kalman filter itself is a base filter. And it's actually an estimator for, makes 2 assumptions. First, all models are linear. And second, all distributions are Gaussians. And under these 2 assumptions, they're actually the optimal thing you can do. There's no better system, and so this is really the optimal solution, but only in the cases of linear models and Gaussian distributions. So let's revisit that. A Gaussian distribution, the Kalman filter assumes everything is Gaussian. This is the form of a Gaussian distribution. You have basically two quantities. You have the mean vector, the mean estimate, and you have the covariance matrix sigma over here. And so the probability distribution about a value x is how far is x away from the mean, weighted with the inverse of the covariance matrix, put to the exponential function. And this gives you these standard Gaussian distributions you have seen over here. There's one example in 1D, and this is in 3D, so if it's ellipsoid in 3D, or you also in 2D, you also get this. This is kind of the Gaussian distribution. And a few properties in terms of marginalization and conditioning of these Gaussian distributions. So given that you have 2 variables, xa and xb, you can split up your variable x into 2 dimensions, or these could even be vectors, multiple dimensions, and they are jointly Gaussian distributed. Then also the marginals are Gaussian distributed, so p of xa, so only considering the first block alone as a Gaussian, only considering the second block alone as a Gaussian. And the other thing is that even if you condition them, so p of xa given xb and the other way around, p of xb given xa are also again both Gaussian distributions. So the marginals are pretty easy because, so in this case, the mean of this Gaussian distribution is the original, the first dimensions of the mean you had in this distribution, and the covariance matrix on this part is just the cut out part of the covariance matrix of your have xa, xb, this was your vector x, and you have the mean was mean a, mean b, and sigma was sigma a, b, ba, b. So this is a form. Then if you look to the marginal only considering the variable xa, so for p of xa is actually the Gaussian or xa with the mean just this value over here, and with the covariance matrix sigma aa, so this term over here. You can just kind of cut out the corresponding part of the mean vector and the covariance matrix. So the marginalization is easy. The conditioning is somewhat more involved. I don't go into the exact details because I can actually easily spend here an hour manipulating Gaussian, an hour, but half an hour manipulating Gaussian distributions. And I'm not sure about how much value this actually adds for understanding that. Okay. Everyone knows what the Gaussian distribution is. So if anything which I tell you here sounds completely novel to you, okay, so that's great. The second assumption we said is the linear model. So the Kalman filter assumes that the motion model, also sometimes transition model, and the observation model or sensor model are linear functions. And they have Gaussian noise with zero mean. So we say the going from xt minus 1 to xt, so this is our transition model, the first one, can be expressed by matrix AT multiplied with the previous state, plus a second matrix BT multiplied with the controls, plus some noise term. So what this, the first part he expresses is how does the system, or the state of the system changes over time if I don't execute any control. So for a wheeled robot, this matrix is typically an identity matrix. If you don't command the robot to drive, it will just stand still. There's no change. Then it's an identity matrix. If you have a flying vehicle, which let's say in an airflow where there's wind, the vehicle may be driving with wind. So even if you don't command, execute any command, the system may change its state. So there are some situations where this matrix A is not an identity matrix. For the standard wheeled robot case, it's typically an identity matrix. And what this matrix B does, it actually maps the controls to like the velocities you command into the system into changes in the state space. Already with the models we described before, you saw that there are sine and cosine functions in there. So it's very likely to be in reality not a linear model, or this reality non-linear. But the Kalman filter assumes we have this linear function. And the second thing is, which the Kalman filter needs, is the observation model. So I can actually compute a predicted observation just knowing the state with the linear function. So given I know what the state looks like, xt, I have a linear function of this matrix ct, which maps that into the observation, to the space of observations. So given I know, or given my state space tells me the robot is here and there's a feature 1 meter right to my right hand side, I need to be able to predict this 1 meter expected observation based on the linear function, which has to be done with this matrix ct, plus some Gaussian noise. These are kind of the assumptions that everything is a linear model, which we have in the Kalman filter. The question about these linear models, or something else I discussed before. Yes, please.
The matrix of observation in the same size with the matrix of the state, or?
No, because the state space and the observation space might have different dimensions. So it's kind of, matrix C should be k times n, where k is the dimensionality of the observations and x the dimensionality of the state.
We don't observe anything in our state space, not, or some part of it, or not completely.
Let's say this way, the way you perceive your observations may be in a completely different space than your state space what you want to estimate. So you may have this range bearing observation where you observe something. You may even say that you have, if this contains the position of the robot and the map of the environment, that you only observe a small part of that, then the observation observes a small part. Well, that the observation observes a small part of it, and then you need to map from the state space to this small subset. So this is definitely not a square matrix. It's k times n, where n is the dimensionality of your state vector, and k the dimensionality of your observation, space of observations. Any further questions about those models? Okay. So just to review them, we had that matrix A that describes how the state evolves without controls or noise. Typically the identity matrix, in a lot of cases. Not every time, but quite often. The second thing that was this matrix B, which is an n times L matrix, where n is the dimensionality of the state vector, and L is the dimensionality of your control vector, which tells you how does the executing a specific control changes the state of the system. So if you, for example, are in a situation there when you have, in SLAM, you want to estimate the position of the robot and the position of all features, and you execute a motion command to the robot, it only affects the position of the robot, not the position of the landmark. So even part of this matrix may be the identity matrix, elements which are not affected, and for some part may not be the identity matrix. So not the whole state vector needs to change, but a subset of the state vector typically changes if you execute a control. Okay. And then we have this matrix C, which is a k times n matrix that describe how to map the state xt into an observation or an expected observation. So what are you expected to observe given that the system is in the state xt? And again, this is a matrix, it's a linear function. And then we had these two terms, epsilon t and delta t, which were assumed to be Gaussian noise terms with zero mean, with the corresponding covariance matrix RT and QT. So RT is here used for the motion and QT for the observation. If you look to the literature, sometimes these are swapped. So, but I'm here in line with the notation of the book where RT is the motion noise, QT is the observation noise. But again, some other descriptions of the Kalman filter change that. So don't be confused. These are just two variables you can use, two names of variables. Okay. So the question is, how does the motion changes, or how does the motion under Gaussian noise, so how do we actually represent the motion model over here into this linear case? So we assume to have Gaussian distribution beforehand. And the question is, the motion also has a Gaussian noise term. So how does this function actually look like? So you can just guess, how could this term look like? So I don't want to make the full derivation of it, kind of influence how this looks like. So this needs to be a Gaussian distribution as well, right? So given we know where we have been before, which command has been carried out, where are we going to end up? So we have this, we have to have this, we have Gaussian noise on the way in the context of this linear function. So let's only look, simplify it a little bit, let's just look to the exponent term, which is the relevant term. Minus 0.5 in my Gaussian distribution. Typically I have here x minus mean, where I'm estimated to be. So how would that look like? It's like, I've been somewhere, apply a linear motion, the equations we had before, where I'm going to end up.
We should put your x minus, ax minus.
Exactly, so this xt minus
ax
a times xt minus 1.
And the controller, so
minus
the bt ut and divided by covariance, I think.
Yeah.
Error.
So which matrix needs to go in here?
It should be the something about the observation. I mean, CT.
Maybe at the motion, but the motion term.
Yeah.
RT minus 1. There's a noise we introduce by making this step forward, kind of motion noise. And then we have the same term again, xt minus a xt minus 1 plus bt ut transposed. So we say the probability of ending up at xt is given where I was before and executing the linear motion. So I take the point where I was before, I propagate it forward, look how far am I away, together with the noise I have in my motion. Okay? And that's where I actually end up with. Okay, let's do the same exercise for the observation. Here dt given xt. So proportional to x of. Means given my molecular state, given I observe something, how likely is that observation given I'm in molecular state? So I need to compare the observation I obtain and the observation I would predict given my state. Minus 0.5 times.
Is that t minus CXT.
Yeah, CTXT
times noise term to the multiplier.
Yeah, QT power minus 1 and then same. Then T minus CTXT. Transpose. That's it. So we have a linear transformation in the motion, the Gaussian noise model, and we have a linear model for computing the predicted observation and the Gaussian noise model. Okay? Okay, now we said our initial belief is Gaussian, this term is a Gaussian, this term is a Gaussian, so everything stays Gaussian. To actually prove that is non-trivial, because we have this integration and we have the multiplication of two Gaussian. This is kind of easy as this integration over here, but I can actually prove that everything is a Gaussian. So if this is in a Gaussian and also the initial belief is a Gaussian, you end up having Gaussian distributions at every point in time. I don't go into the detail, it's kind of a 2 or 3 pages derivation why this is the case. If you're interested in that, you find this, for example, in the probabilistic robotics book. There's a book, there's a section on the derivation of the Kalman filter, and it will go into details to actually show that this is the case. But I kind of dropped that. So just to summarize, what do we have? We have linear motion, which makes a prediction of where we are going to end up with. And we start with the Gaussian distribution, we end up with the Gaussian distribution. And the second thing is we estimate what should we measure and what do we measure and compare that under the Gaussian noise model. And this we use to multiply is with the prediction and then come up with a Gaussian estimate. It's kind of these steps clear. Are these steps clear? Okay. This leads us to the Kalman filter algorithm. Let's go through it step by step. The first 2 lines, the second or third line, sorry, are the motion. So this is the mean. So this is these bar lines here is the predicted state. So I say the predicted mean of my estimate is the mean I had before. So AT times the mean estimate I had before, plus BT times UT. So how does it change? So this is again the standard motion model. The second line over here tells me how do I need to update the covariance matrix. Because the thing is, how does a Gaussian distribution changes under a linear function with Gaussian noise? This turns out to be this term over here. If you go to the most simple case where A is the identity matrix, so if A is the identity, these two terms simplify to the new mean, the old mean, plus BT times UT. And the uncertainty stays the uncertainty I had before, plus the uncertainty I need to add according to the motion. So I have my original uncertainty, my covariance matrix, I make a step forward so it slightly increases. This is exactly what's written over here. And so if AT does some transformation so if AT, for example, scales some weird system where you have a scaling factor where the size of the space grows over time, then the uncertainties would grow accordingly. So it's depending on how not applying any motion changes my state, also the covariance matrix needs to be transformed accordingly. And these equations result from how does a Gaussian change through a linear function with Gaussian noise. That's just what comes out of that. Again, if you want to go into the details, it's quite some derivations of how you end up with. My goal is here to give you an understanding of the individual quantities. The second block down here, line 4 to line 6, is how does the prediction step work? Again, so what happens here is we have our predicted noise. What we're going to do is we compute an expected measurement. This is this term over here. Where I have CT times the mean. This gives my predicted measurement. And I'll look, what's the difference between my my expected measurement, my real measurement, sorry, and my expected measurement. And if they are perfectly in line, they perfectly match. So I exactly observe what I expect. This term here is 0. So the mean stays the predicted mean. which makes sense. So I make a prediction. In my prediction, I'm perfectly in line with, I expect exactly, what happens is exactly what I expect, so I don't make any change to the system. If this, however, is not the same, so I observe something, and for my observation that I should be 20 centimeters to the right-hand side, this term, so this K here, which is called the Kalman gain, which is completed this way, which basically trades off the accuracy of my prediction I had before and the accuracy of my observation, and kind of weighs on how much I do the update. So if I have a very, very, very accurate motion and a very inaccurate observation, I go somewhere and I measure something which is far away from what I expect. I may say, yeah, my observation is so noisy, my motion is so accurate, I basically trust my motion and just will update it very little bit into the direction of my observation, because I trust the motion much more than my observation. If it is the other way around, that I say, my motion is rather noisy, but my observation is super, super accurate. If I make my step forward, I see that there's a mismatch between my motion and my observation. I say, my observation is so great, so good, I trust my observation a lot, so I move a lot into the direction where I should be according to the measurement. And this trade-off exactly computed by this Kalman gain. So it kind of weighs the uncertainty I have with the uncertainty of the observation. So the uncertainty of the prediction, this one, and the uncertainty of the observation. And then the new covariance matrix is updated accordingly. Again, here the Kalman gain, it's the identity minus the Kalman gain in this observation matrix here. It takes into account. So if I know perfectly where, for example, this landmark is I'm observing, and I know my observation is very accurate. Although my motion, the noise I currently over half I suppose is very large, it will dramatically shrink because my observation tells me very accurately where I'm relative to that landmark, and I know where the landmark is quite well. This is kind of what happens in the upstate step, and then the mean and the covariance is referred. So one can actually go to the details in how this is derived. You can actually derive all that from three basic things: the marginalization of a Gaussian, the conditioning of a Gaussian, and how a Gaussian changes under affine transformations. And by using these three steps, you actually derive all these equations over here. Again, this is somewhat involved. You can easily take an hour to do that here, therefore I skip that, because I don't think it really adds a lot to the understanding. But this is a way you need to update your system if you have Gaussian distributions and linear models. Okay, you can see there's a small example. So let's say you start somewhere, you make a prediction step, and this is kind of the prediction where your system will be the Gaussian distribution. Then, so this is kind of the bold one is always a new one, which is standing here the measurement, and the red one is the what we had before the prediction. So I take a measurement. This is this guy over here, the green one, which is kind of, let's say, what my measurement tells me, where the system is given that measurement. And then I perform a correction which weighs the prediction and the prediction step, the red one, and the measurement, the green one, into this joint one, which is here given by the blue one, which is a multiplication in this case of these two terms over here. And it's weighed by the Kalman gain. How much more do I trust the observation, and how much more do I trust my motion? So what you end up here is really a weight mean of these two distributions. And this weighing factor comes from the Kalman gain. And then you just repeat that process. So this is what we had before. We make another prediction. So here the system was approximately in this state, and kind of, for example, I move forward, and it gets more uncertain because while I move, my Gaussian distribution, the variance increases. So I have this pink curve over here. Then I get a measurement. This measurement is here shown by the cyan curve, and I can combine that and get this here yellow curve, which is the corrected one. So always stay in this Gaussian distribution. I move forward, I get more uncertain, and then I get an observation that typically makes me more certain. And this process is repeated over and over again. So this is kind of what the standard vanilla Kalman filter does. Okay, the Kalman filter made two assumptions. The first assumption was that with Gaussian distributions, and the second in noise, and the second one was that we have only linear models, so motion model, observation model was linear. So what happens if this is not the case? It's a key thing, because if you think about the robot we had before, we have the angle involved, and we have a rotational velocity and a translational velocity, especially the rotational terms are non-linear components, so they lead to non-linear functions. So in basically all realistic problems, these assumptions are violated. So we have non-linear functions. And so the idea is to actually extend the Kalman filter to the so-called extended Kalman filter that provides us a tool for dealing with the fact that we have non-linear models. So we kind of get rid of the assumption that we have a linear model and assume we have some function g which tells us how to go from xt minus 1 with ut to t, and we have an observation function which maps our xt to the state of our observations. In the extended Kalman, in the Kalman filter case, these were linear functions. This g and h were linear functions. The extended Kalman filter says they are not linear functions anymore, so they can be non-linear functions. Let's see how what changes. Okay, so what you see in this plot is how does a function change the Gaussian distribution. So you see down here you have a normal distribution, and this is a function. In this case, it's a linear function. How does this linear function actually change this Gaussian distribution? If this is a Gaussian, this is a linear function, you make this transformation, this is a transformed Gaussian distribution. It's still a Gaussian distribution, because this is a linear function. Now, let's see what happens if we use a nonlinear function. If this function is not a line anymore, but it's a nonlinear function which looks like this blue curve over here. So we take this Gaussian distribution, transform it under this function, so we map the mean exactly to this point. We map this term over here to this point. We map this term over here to this point. If we do that, we end up with this multimodal, approximately bimodal distribution. This is far away from a Gaussian. So this guy here is not a Gaussian distribution anymore. And this is a problem we have. If we allow for nonlinear functions, and I transform the Gaussian distribution, it's not longer a Gaussian distribution anymore. This breaks the Kalman filter. This is the main problem we have in here. So nonlinear functions lead to nonlinear to non-Gaussian distributions under the transformation, and then the Kalman filter is not applicable anymore, because after the first step, after the first motion update, we don't have a Gaussian anymore. That's bad. So how can we resolve that? And one of the ways to resolve that is to say, I take my nonlinear function, but I locally linear, or I linearize it into a linear function given the current linearization point. So you can actually do local linearizations to come up with it. You should know that from your basic math courses, terms like a Taylor expansion, something you have a nonlinear function, you linearize it around the point you're interested in, and then use a linear function in order to do the motion or the predictions. So we can do it in a linearized form. What do we need to compute if we do a Taylor expansion?
The hashing of the matrix.
First derivative, you really need the Jacobian would be the corresponding derivative in vector form. Exactly. So because you take your point, you look to the gradient you have there, so the first derivative is Jacobian in the general form in the high-dimensional space, and use this Jacobian as in order to come up with your linear function. Okay. So we can express this as the prediction set. We have our nonlinear function g, and we want to estimate the new pulse xt given xt minus 1 and ut, so control command. We can say this is a function evaluated at one point around the evaluated at the previous estimate we had, ut, and then times the first derivative, and then the difference on how far am I away from my linearization point. So I linearize in ut minus 1, and I evaluate the function at ut minus 1, and then I compute the first derivative at that point of the function, and then say how far am I away from my linearization point, and this is then a linear function again. So this is kind of the linearization. So gt depends on the current state the system is in. So depending where you are in your nonlinear function, you will get a different linearization. Oh, and this is this GT, this term here, is the Jacobian matrix, or Jacobian of this function G. So it's kind of the first derivative if you are in a high dimensional space. So first derivative, as you may know from school, 1D, everything is easy. If you have a matrix, you have these partial derivatives in the individual elements of the matrix. And this exactly the same holds for the correction step. So I have my function, my observation function, HT, which is nonlinear. I say I evaluate this function at the current predicted mean after the prediction step. This is mu bar over here. And then I compute Jacobian and say how far is my away from this predicted mean. Okay, just for those of you who may have forgotten what the Jacobian is, the Jacobian is given you have a function G, which has the components G1, G2, Gm. So, and these x can also be higher dimensional inputs of the function. The Jacobian matrix is defined by the partial derivatives of the individual components of this function G with respect to the individual dimensions of the value x. So G1, so the partial derivative of G1 with respect to x1, G1, x2, G1, xn, and this for all the components. So it's an m by n, m. So this is swap m by n matrix. Okay, kind of clear. Any questions about this? How to repeat that? Okay, perfect. So, and just as an illustration, you can see this Jacobian as kind of the gradient as it wasn't for the 1D case, but in the multidimensional case, you kind of get that plane along this kind of surface. And this is kind of your linear approximation, or this your linear approximation of that function at that point. Okay, so this is nice because now these guys here are linear functions, computed for every term for every point individually, but we have linear functions. Okay, so we have again our transformation of our Gaussian. So we had it before. So if it's a linear function, everything is great. We go in with a Gaussian, we come out with a Gaussian. Perfect. Okay. Now we have this nonlinear function as I had before. So exactly the same example. This is the mean estimate over here. If we transform this Gaussian distribution under this nonlinear function, we end up with this weird curve over here, which we can't deal with the Kalman. Okay, so what is the Kalman filter doing? It linearizes this function here around the mean. So this is my linearization point. So we'll compute the first derivative here, which will look something like this, and then use this as a linear function to transform this Gaussian. So this is what it looks like, the red one over here, and it transforms the red one, and then we end up with this red curve over here. If we would really take every point, let's say, compute for every point here the transformation, and then recompute the Gaussian distribution from this transformed point, we'll come up with the blue curve. But in reality, if we use our linearization, we come up with a red curve. So there's a mismatch between the true, if I take the transformed points and compute the Gaussian of that, I would end up with a blue curve, but I come up with a red curve. So there's a mismatch. And the more nonlinear the function is, the bigger it is. And it also depends on the input uncertainty I have. So if you look at this Gaussian, you can see the difference here between them. If I transfer another Gaussian, which is here, has a higher uncertainty through this nonlinear function, then actually the mismatch between the blue and the red curve gets bigger. Because the bigger the uncertainty is I have in here, the further away the points are from the mean that I need to transform. And the further away from the mean, in general, the worse the approximation gets of my linear function. So if I have a very small uncertainty, the error I do by linearization is typically small. The bigger the uncertainty gets, the bigger the error gets in general as well. Okay, here was one example where exactly I have a quite peak distribution over here, transform it through the same function, then you can see that the mean the Gaussian estimate here, the red and the blue curve are pretty similar. Okay, so how does it change the Kalman filter? I have now my linearized motion model. So there was a thing before the linear case, which is here still on the blackboard. So this was the motion model and the observation model for the perfect linear case. Now we replace these terms over here, and this term over here, by our nonlinear function. By our linearized functions, sorry. So this is exactly this is our linearization point, and then our Jacobian, so this is kind of a linearized motion model. So the equation stays exactly the same, except that I have to replace the, in this case, the a t mu t minus 1 plus bt ut by this term over here, which is again a linear function because the linearization of my nonlinear function. I can do exactly the same for the observation model. Here I replace my c times mu bar t, which is my linear prediction, using the linearized version of my nonlinear function. And then again I have linear update. That's it. I'm more or less done. So this was the extended Kalman filter. This is the extended Kalman filter, and the only thing which changes with respect to the Kalman filter is that I here have my function g, and here I have my function h, and what also changes, so I have to transform this my uncertainty, my covariance matrix here, also by the Jacobian. This was pretty similar to what this A matrix was doing before. Since A matrix doesn't exist here anymore, it's replaced by the Jacobian. And the same holds here. So the matrix CT for the observation is replaced by the Jacobian of it. So here, at this point, we had before had the C, but now the H's, and we had the A where the G was, but the rest is the same. This is kind of the extended Kalman filter. The only thing the extended Kalman filter does is I have these nonlinear models, which I can't deal with because they would destroy my Gaussian distributions. So what the extended Kalman filter does, it says, I take my nonlinear function, I just linearize it around the mean, compute it with the Taylor expansion by approximating with the linear function, and then do everything with my linearized model. And I perform my Kalman filter on this. Since these functions are now linearized, so they're linear functions, my Gaussian distributions stay Gaussians, and I'm happy. So you can see this as kind of a ad hoc solution, you also call it a hack if you want to deal with these nonlinear functions, because the Kalman filter simply, by definition, is restricted to these linear functions. And the best thing, but one thing you can do, so just I assume my nonlinear function is at least locally linear, say everything is local and do that. Of course, the EKF is not the optimal estimator. The Kalman filter has this property of being optimal for the linear case with Gaussians. But if you're back in the linear case, the EKF gives the same result than the Kalman filter, because if you linearize a linear function, the Jacobian is 1. So nothing changes in here. So for the linear case, it's still fine to use the extended Kalman filter, but as soon as your functions become nonlinear, the extended Kalman filter is not an optimal estimator. Exactly. So, and the key thing is the extended Kalman filter. As long as your functions are not too far away from a linear function, and your uncertainty is not too big, it works quite well. The bigger your uncertainty gets, and the more your nonlinear function becomes nonlinear, the worse your estimates get. It can be arbitrarily bad, depending on the properties of your problem. The Kalman filter is also complexity-wise to take into account that the complexity of the Kalman filter is quadratic in the dimensionality of your state space, so 1 update instead, and it's approximately cubic in the k, which was the dimension of your measurement. This is the fact that you need to invert the function where the measurement is in, which was the dimensionality of the measurement. And a naive inversion takes cubic time. There are efficient ways for inverting a matrix, and the best one is around k to the power of, or n to the power of 2.4, but it's still approximately cubic. So that's the complexity. If either your the dimensionality of your observations increase dramatically, you have a problem, or if the number of states you got to represent increases, you get a problem. Because at some point in time, it may not become tractable or computationally tractable anymore. It's going to be properties of the EKF. Okay, are there so far any questions about the Kalman filter or the extended Kalman filter? Okay, so my goal of the lecture today was to introduce you to the concept, what are the assumptions the Kalman filter and extended Kalman filters do? I hope you understood these assumptions. How they deal, or why these assumptions exist, in terms of Gaussian distribution in linear models. The reason was because otherwise, if I would use nonlinear functions, my estimate is not Gaussian anymore. And then I can't use just the mean and the covariance matrix to represent my distributions. And how actually, or which adaptation the extended Kalman filter does in order to be able to deal with nonlinear functions. I don't expect you at the moment to understand every single line of the Kalman filter algorithm, why these matrices are multiplied in this way. This is something which actually comes if you go through the derivation of the Kalman filter, which you'll find in the probabilistic robotics book, or even a more compact way in the work of Schön and Lindstern, manipulating the multivariate Gaussian density. The link is on the website. So all the material here you actually find as PDF files on the website except the book. And this kind of nicely shows also, based on the marginalization conditioning and the affine transformations, why you end up exactly in this form of the Kalman filter. And there's also a Kalman filter tutorial by Walter Bischoff, which is kind of nice to read if you want to look more to the details. But so I use probabilistic robotics book in order to make the slides, so all the notation should be consistent with the book.
Yeah, one question just for clarification.
Yeah.
This xt vector, this state vector,
yeah.
State is still just position and orientation.
So it depends. So far I said it's the general framework for state estimation, whatever you want to estimate. If you just want to localize a vehicle, that means you know the position of the landmarks in the environment, for example, then it would be just the x, y, and theta. If you want to do the SLAM problem, where you also want to estimate, for example, the location of the landmarks, your state vector increases dramatically because it's x, y, theta, the position of landmark 1, the position of landmark 2, the position of landmark 3, and so on and so on. So the more landmarks you experience in your world, the bigger your state vector gets. And therefore, this quadratic complexity in the number of landmarks is typically the limiting factor in the Kalman filter, because you always observe things locally. The dimensionality of your observation is typically small in most cases, so that's all fine. But the limiting factor is really the number of landmarks. It's quadratic in the number of landmarks every update step. That's the problem. Or at least if you go to large environments, that's the limiting factor. Are there any other questions? Okay, so perfect. Then we are done for today. I hope you understood the key concept of the Kalman filter and the extended Kalman filter. If not, go through the book or one of those tutorials, or visit me in my office, and I will try to help you as good as I can to make that understandable for you. Because we will need the details of the Kalman filter, especially the extended Kalman filter, next week, when we really dive into how to do SLAM with the extended Kalman filter. And also the homework of this week, but next week, will be the realization of an extended Kalman filter-based SLAM system. So if you have any questions, you can ask them either to me, you can ask Nicola and Rainer in the exercise on Wednesday. Whenever you need some help, let us know, and I hope you understood it. And if not, let us know, we will try to fix it. Okay, thank you very much.